Hi everyone. Having gone through alcohols, phenols, now we are left with ethers. So today's video lecture will be based on ethers, its methods of preparation, general methods of preparation, physical as well as the chemical properties of the ethers. So coming to the heading, that is the ethers. First of all, let's define what is the functional group of ethers or the ethereal group. So any organic compound in which oxygen is bonded to two carbon atoms. So we have compounds of type ROR prime. So these type of groups, carbon, oxygen, carbon. These types of groups are known as ethers. Now, in these ethers, these are maybe alkyl group, maybe aryl group, or both the R and R prime may be same or may be different. So look at this. If R and R prime, if R and R prime are same, then we say this is symmetrical ether. Example, look at this. CH3, OCH3, C2H5, OC2H5. These are known as symmetrical ethers. Or we can have a look at this. C6H5, OC6H5. These are known as symmetrical ethers in which both alkyl groups or aryl groups are same. If R is not equals to R prime, then these types of ethers are known as unsymmetrical ether. Take these examples. CH3, O, C2H5. So this is what we call as unsymmetrical ether. The groups are different. We can have a look at this. CH3, CH3. That is isopropyl group, and C2H5. Or we can say look at this. CH3O, C6H5. These are known as unsymmetrical ethers. Symmetrical ethers or unsymmetrical ethers. Now these ethers, if we have aryl group, when this is aryl ether. If we have only alkyl group, we say this is alkyl ethers. Depending on the group, we can have R as well as aryl group. If we have a combination of aryl and alkyl, we say this is aryl alkyl ether. Now coming to general structure of ethers, we have look at this. R, O, R prime. The carbon of alkyl group, that is R or R prime, that is of sp3 hybridized, and this oxygen, the central atom oxygen through which two alkyl groups are attached, this central atom oxygen is sp3 hybridized. So central atom oxygen being sp3 hybridized, the geometry of this ether will be tetrahedral, but the shape will be angular. Geometry is tetrahedral, shape will be angular. Now the bond angle between ROR, so this carbon is also sp3 hybridized, this carbon is also sp3 hybridization should shape is R R. So we have two lone pairs of electron on the central atom. This bond angle is greater than tetrahedral angle 109.5 degree and is approximately 111 degree cent. Now why this angle is greater than tetrahedral angle of 109.5? The reason being due to the steric hindrance of these two alkyl groups. These undergoes steric hindrance. The bulkier group, that is R and R prime, because of this steric crowding between these two bulky groups, the bond angle which was supposed to be tetrahedral 109.5 is greater than this tetrahedral angle and is about 111. So the reason is because of this steric hindrance. So this is about the general structure of ethers. Now coming to general methods of preparation of ethers. General methods of preparation. First one, internal dehydration of alcohols. That is, from alcohols, dehydration of alcohols. Now this was one of the chemical properties of alcohol that we have discussed in previous lectures. So alcohols, these alcohols ROH on reaction with sulfuric acid concentrated at low temperature So low temperature means temperature less than 140 degrees centigrade. So dehydration of alcohols with concentrated sulfuric acid at low temperature, that is 140 degree, gives you ethers. So by this method we get only symmetrical ethers. Now this reaction, for this reaction, this is base yield is obtained if R is primary. So look at this, we have this CH3OH methanol on the reaction with concentrated sulfuric acid at temperature less than 140 degrees centigrade. When this gives you CH3OCH3, dimethyl ether plus water is formed. C2H5OH, by use of same reagent, sulfuric acid concentrated at low temperature condition, when this gives you diethyl ether. So dehydration of alcohol at low temperature gives you ether. Now if the temperature is more than 140 degree, then also dehydration takes place, but the final product will be alkene. Alkene will be forming as a major product. So we have to carry out this dehydration reaction below 140 degrees centigrade when the major product will be the ethers. So this is one method of preparation of alcohol, ethers from alcohol, which is a chemical property of alcohols. Then the second method for preparation of ether is from alkenes. Preparation from alkenes. In these alkenes we have different methods. First reaction is addition of alcohols in presence of acid. So we have looked at it starting with alkene. Alkene reacts with alcohols in presence of mineral acid. So reaction of alkenes with alcohols in presence of acid, when this gives you ethers. So if you look at this reaction follows Markovnikov's addition. The reaction follows Markovnikov's addition rule. Since the reaction follows Markovnikov's addition rule, this reaction must proceed by formation of carbocation. So if there is a formation of carbocation, the carbocation has got a property of rearrangement. If carbocation has a property of rearrangement, then there is a possibility of rearranged product that is formed in this method of addition of alcohols to alkenes. Take this. We have started with CH2 double bond CH2. This reacts with methanol in presence of acid. Now both the carbon of alkene is symmetrical, so there is no question of Markovnikov's rule or anti-Markovnikov's rule. We get this CH3 CH2 OCH3. This is the ether. But if we take this CH3 CH double bond CH2, we have unsymmetrical reagent reacts with unsymmetrical reagent. The reactant is unsymmetrical, reagent is also unsymmetrical, so we have to follow Markovnikov's addition. So if you look at this is the positive part, this is the negative part. So rule says positive part goes to carbon with more hydrogen, negative part goes to carbon with less hydrogen. So the product is CH3 CHO CH3 CH3. So this is the Markovnikov's addition. Or take this. Suppose we have this alkene. This reacts with C2H5OH in presence of mineral acid. So look at this. Again, this will follow Markovnikov's addition. So this is the major product that is formed. So acid catalyzed addition of alcohols to alkenes, reaction follows Markovnikov's addition, carbocation intermediate, and there is chances for rearrangement provided if carbocation can undergo rearrangement. So this is a method. Now I'll show you some examples of rearrangement also. Take this reaction CH3CH CH3 CH double bond CH3. If this reacts with methanol in presence of mineral acid, first secondary cation will be formed. This secondary cation will undergo rearrangement by hydride shift, so that this is converted into tertiary, and finally tertiary reacts with alcohol to give you the major product. So this is the final product that is formed. So carbocation followed by rearrangement, that is by hydride shift. Take this example also. CH3 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 CH double bond CH2. If this reacts with methanol in presence of mineral acid, In the first step, there is a formation of secondary carbocation followed by methyl shift to give a more stable tertiary carbocation. So the final product will be CH3. This is the rearranged product. So these type of rearrangement is possible only when there is a carbocation intermediate, because carbocation has got a very important property of rearrangement. So we have to keep in mind, in addition of alcohols to acid to alkenes, so the addition of alcohol in presence of acid to alkenes, reaction being carbocation, there is always chances for a rearrangement. If there is no question of rearrangement, then only one product will be formed, that is the Maser product. So this is first method, that is addition of alcohols to alkenes. Next method is a name reaction This is known as alkoxymercuration demercuration. Alkoxymercuration demercuration reaction. So this is a combination of two reactions. First one is alkoxymercuration. The next one is demercuration. So this involves two reactions. So look at this. We started with alkene. Alkenes react with alcohol in presence of mercuric acetate. This is mercuric acetate. So reaction of alkenes with alcohol in presence of mercuric acetate. First, alkoxy group is added. Minus acetic acid is removed. So this step, addition of alkoxy group to the double bond of alkene in presence of mercury, this step is known as alkoxymercuration. So mercury and alkoxy both are simultaneously added, and this step should follow Markovnikov's addition. And finally, look at this. This mercury group is to be removed, and for this we use a reducing agent, sodium borohydride. When hydride of the reagent, sodium borohydride, will replace mercury group here. So COR, single bond CH. So this H is coming from this reagent. So this step is demercuration step. If you look at this reactant and the final product, this reactant to the final product, this is reactant, this is final. So coming from reactant to the final product, if you look at it, it is simply addition of ROH. So again we add alcohols to alkene to give you ether, but this alcohol addition again follows Markovnikov's rule, but there is no rearrangement. So in this process there is no formation of cation, simply addition of alcohol in presence of mercuric acetate followed by reduction with sodium borohydride. But the question is, this addition, alkoxy group is coming from alcohol, but this hydrogen is not coming from alcohol. This hydrogen is coming from the reducing agent, that is sodium borohydride, that we have used for reduction of this mercury group. But the overall reaction seems to be simply addition of alcohols to alkenes, and the reaction must follow Markovnikov's addition, and there is no question of carbocation formation. Hence, no rearrangement is possible or no rearranged product will be formed. So look at this reaction. We have this reaction. Let's take this same mechanism also. So we have this alkene. So alkene reacts with alcohol in presence of acid, rearranged product. But if we carry down this reaction in presence of mercuric acetate followed by reduction sodium borohydride. No doubt reaction is Marconi Cross addition, but there is no question of rearrangement. So the first step is alcohol in presence of mercuric acetate followed by reduction with sodium borohydride. So the product form is CH3, 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 O. CH3. This is Marconi-Cross addition of this. So the same alkene can be converted into two different ethers depending on the choice of reagent that we use for reaction. So if we simply add alcohol in presence of acid, rearranged product. Adding of alcohol in presence of mercuric acetate followed by reduction, we are getting another ether, but there is no rearrangement product. In both the case, there is a Marconi-Cross addition. Take this again. If we react this first with methanol in presence of mercuric acetate followed by reduction sodium borohydride, then the product is CH3, CH, CH3, CHOCH3 and CH3. Again there is a Marconi-Cross product, but there is no rearrangement here. So this is how we carried out addition of alcohols to alkenes, in which both follows Marconi-Cross, but one there is a possibility of rearrangement of cation, the other one there is no possibility of rearrangement of cation. So these are the methods of preparation of ethers from alkenes. Then we have a more important named reaction that is also often used as a very good source for preparation of ethers, and that method is from alkyl halides. So let me rub this portion. Next from alkyl halides. Alkyl halides. Now this reaction is a very well known reaction known as Williamson ether synthesis. Williamson ether synthesis. Now in this reaction we use a combination of alkoxide ion and alkyl halide. So we have look at this R prime O minus sodium salt or potassium salt of alcohols, that is alkoxide ion. These reacts with alkyl halide via SN2 pathway substitution nucleophilic bimolecular. This alkoxide group O minus attacks this electrophilic carbon, and from this X minus leaves the system, and this gives you R prime O R plus NaX here, KX will be formed. So look at this. In this reaction, reaction is SN2. So SN2 reaction requires that these alkyl groups present here, these alkyls must be primary and sometimes secondary. It's better to use primary alkyl halides only. If we use secondary or tertiary, then the major product will be elimination reaction. So one or sometimes secondary, but the base yield should be by use of primary alkyl halide, and this is alkoxide, and this alkoxide can be primary, secondary, tertiary, whatever may be, but this alkyl should be primary with secondary ether plus alkene will be formed. So ether by SN2, alkene by E2. If we use tertiary, then the major product will be alkenes. And why? E2 reaction. So we should avoid using secondary alkyl halide and tertiary alkyl halide for this Williamson ether synthesis. So let's see the reaction here. Suppose look at this, we have this reacts with CH3, CH2Cl, we have alkoxide ion, we have alkyl halide, or the second combination is we have this CH3, CH2, O minus, Na plus. Now this reacts with alkoxide, alkyl halide, alkoxide, alkyl halide. The difference is, in the first case alkyl halide is primary, in the second case alkyl halide is tertiary. This first reaction, in this first reaction, since the alkyl halide being primary, the major product formed will be ethers. That means this will attack this carbon, and from this Cl minus will be released, and this gives you C2H5. But if we take this second reaction, that is ethoxide plus tertiary butyl chloride, this carbon being tertiary, this is surrounded by 3 bulky groups. As a result, this nucleophile cannot approach this electrophilic carbon. So if this cannot approach electrophilic carbon, then this will undergo elimination reaction. If this undergoes elimination reaction by E2 pathway, then this gives you the final product, that is alkene. This is the final product that is formed. So we have to be very careful while preparation of these ethers by use of Williamson ether synthesis. Alkoxide, you can use any alkoxide, either the alkyl is primary, secondary or tertiary, but the alkyl should be primary only. If alkyl is of alkyl halide is secondary or tertiary, then the reaction may shift to elimination, in which alkene will be forming as a major product, ether will not be forming as a major product. So this is the difference between these two. Look at this, if we use this phenoxide ion, O minus Na plus CH3 CH2I, then this will attack this carbon, and this I minus region, this will give you aryl alkyl ether, aryl alkyl ethers. But if we use this CH3O minus react with aryl halide, then no reaction takes place. As we have discussed in alkyl halides, aryl halides, carbon is sp2, so sp2 carbon X bond becomes a stronger bond, is not easy to break. Second, carbon halogen bond appears double bond in character due to resonance coming from the lone pair electron of halogen. Again, because of this carbon CX bond being a double bond, carbon bond becomes much stronger. So there is no question of breaking of this CH bond. And since this reaction requires SN2, so SN2 reaction requires a rear side attack. But due to the presence of this ring, a rear side attack is prevented. So this reaction cannot take place. That means we cannot use this aryl halides for preparation of ethers. Similarly, if we take this alkoxide ion and vinyl halides, again same, carbon is sp2, so sp2 carbon halogen bond is stronger bond. Similarly, we can also have a resonance the same as that of halobenzene. So these again the reaction does not takes place, no reaction takes place. So for this requirement is we should have an alkyl halide, not aryl halide, not vinyl halide, but we can use aryl halides. CH2 double bond CH2X. We can use this aryl halides, and this gives you CH2 double bond CH2OCH3. So vinyl and aryl halides cannot be used for this Williamson ether synthesis of ether. So these are some of the methods by which we can prepare ethers. That is general methods of preparation of ethers, and I am going to use some important merits as well as demerits of this reaction and this examples along with their example. So these are methods of preparation of ethers. Now after having discussed this methods of preparation, now we come to the general chemical properties of ethers. Now coming to chemical properties of ethers, first is a reaction with mineral acids under cold condition. We have looked at this ROR prime. This may be symmetrical ether or this may be unsymmetrical ether. Oxygen of ether contains two lone pairs of electrons, so this can act as a basic site. So this base reacts with H plus ion to give you simply salt. Simply salt formation. So inorganic mineral acids react with ether under cold condition to give you salt. Take this example. R prime react with Hi when this gives you I minus. If this reacts with sulfuric acid, then this gives you sulfate, etc. So reaction of ethers with mineral acids under cold condition gives you simply salts. But if we react these with HS followed by heating, then these undergoes cleavage of ROR bond. with hot and concentrated Hi. So look at this. this ROR prime reacts with HI followed by heating, when this gives you Ri plus R prime OH or ROH plus R prime I, depending on the nature of R and R prime. This reaction may proceed by SN1 or by SN2 depending on the nature of R and R prime. But if we take excess further react with HI, then this alcohol will also be converted into alkyl iodide. So if we take one equivalent of HI, then we'll get alkyl iodide and alcohol. But if we take excess of HI, then both will be converted into alkyl iodide. So as I told you, this breaking of this RO bond or R prime O bond, these may follow SN1 or SN2. So we need to understand which mechanism should be followed for breaking of this RO and RO prime bond. So look at this. We have look at this ROR prime. First this reacts with H plus ion from HI. So ROH plus R prime. So these may undergo SN1 or SN2 depending on. So this is step 1. Step 2. See, if R prime is tertiary, if R prime is tertiary and R is primary, so we have a combination of tertiary alkyl group and primary alkyl group, then the reaction is ROH plus R prime. So this undergoes reaction by SN1. So if any of this alkyl group happens to be tertiary, then the reaction will proceed via formation of cation, that is known as SN1. So we have this ROH plus R prime plus, and this R prime plus will combine with I minus to give you R prime I. That means if we have a combination of primary and tertiary alkyl group in this ether, then on reaction with HI followed by heating, means we are taking only one equivalent, so the iodide will be coming from the tertiary and alcohol will be coming from the primary, and the reaction will be via SN1. But if R and R prime both are primary, then the reaction will follow SN2. So we have this R prime with a positive charge on oxygen. This reacts with I minus. So this will undergo either attack from R or attack from R prime. SN2. So this will give you Ri plus R prime OH or ROH plus R prime I, depending on the spherical aspect of R prime and R. So if R contains one carbon, R prime contains two carbon, then either will be from the one containing less number of carbon atoms. If the carbon atom increases, steric hindrance increases, chances for SN2 reaction will minimize. So take up this example. CH3O, CH, CH3, CH3. Now these react with HI, one equivalent, followed by heating. Now look at this. This is primary, this is secondary. Primary, secondary. Now secondary may give you a more stable secondary cation, so the reaction will proceed by SN1 and alcohol will be coming from primary and alkyl halide will be coming from secondary. If we have look at this CH3, CH2O, tertiary butyl, so we have to break this bond. Now this is tertiary, this is primary, so reaction will be SN1. So the product is tertiary will give you iodide and the primary will give you alcohol. But if we have this reaction, look at this, CH3O, C2H5, this reacts with HI, one equivalent. Then look at this, both are primary, this is also primary, this is also primary, then the reaction has to be via SN2. If reaction is SN2, as I told you earlier, I minus will attack that carbon atom of alkyl group having less number of carbon. So we have one carbon, we have two carbon. So this means sterically hindered, I minus will attack this and we have to break this bond. So we have CH3I plus C2H5OH. So in case of SN2, iodide will be going with that carbon, with that alkyl group having less number of carbon atoms. So this is reaction with whole and concentrated. But if we take a combination of alkyl and aryl halides, this reacts with HI. This reaction, whether we have primary, secondary or tertiary, this bond, alkyl oxygen bond, will always break. If this breaks, this is primary, so reaction has to be SN2 and this will give you phenols plus alkyl iodide. So reaction of alkyl aryl ethers will always give you alkyl halide and phenol. So take this word. But the mechanism may be SN2 or SN1 depending on the nature of alkyl group. Take this. This is alkyl, this is aryl. Again we have to break this bond. Reaction with HI. So since the alkyl being tertiary, reaction will be SN1. So we have phenol plus tertiary alkyl iodide. But if we have look at this, both aryl group, if this aryl ether is heated with HI, no reaction takes place. The reason being, this cannot undergo reaction by SN1 as well as SN2. Why this cannot undergo SN1? Because benzene cation does not form, because this is very unstable. So why this cannot undergo SN2 reaction? Because of the presence of ring, the rear side attack is totally prevented. So if we have this aryl which is bonded to ethyl oxygen on the reaction with HI followed by heating and even a very high temperature, also no reaction takes place. Take this. This is aryl. We have look at this. This is cyclic ether. If we heat with this HI, also no reaction takes place because we cannot have SN2 as well as SN1 at this carbon. This being a bridgehead, due to the presence of this bridge, real side attack is prevented, so no SN2. Bridgehead carbon cannot assume planarity, so there is no question of formation of carbocation, so no reaction takes place here. Or if we have this type of, look at this, in which we have this both, but if you look at it, this is a tertiary, and if we hit with this HI again, no reaction takes place. So every tertiary alkyl group will not react, only the open chain will react. If we have a bridge carbon, then no SN1, no SN2 reaction is possible. But if we have, look at this, suppose we have this, if we have, this is open chain, this is cyclic, so we can break this open chain is tertiary, so we can break this. If we break this bond on heating with HI, this gives you this alcohol, plus this will be converted into iodide. So this is how we break this alkyl oxygen bond or aryl oxygen bond in case of ethers on heating with this HI. So we have to be very careful. By looking at the group, we have to identify what is the major product if only one equivalent of HI is formed. So reaction may be SN1, may be SN2, depending on the nature of R and R prime. So this is one of the most important reaction of ethers, that is cleavage of carbon oxygen bond. Now if these ethers ROR prime is made to react with steam, that is we have to use steam, then both will be converted into alcohols, ROH plus R prime OH. Take this CH3O C2H5 reacts with H2O steam, when this gives you methanol and ethanol is formed. If we take this also, then both will be converted into, one is converted into phenol, the other one is converted into alcohol. So this is how this carbon oxygen bond is to be taken in case of reaction with concentrated acids followed by heating or by reaction with steam. So this is the most important reaction of ether, it is cleavage of carbon oxygen bond, and cleavage depends on the nature of alkyl group or nature of alkyl or aryl group, and the mechanism may follow SN1 or SN2. Again, this depends on the alkyl group nature, either we have a primary alkyl group, secondary alkyl group or tertiary alkyl group. So this is some of the reactions of ethers that we often come across. Now if we have aryl ethers, then these aryl ethers may undergo nucleophilic substitution reaction. So we have this, if suppose we have this, that is aryl ether. So these alkoxy group, we have oxygen with two lone pairs of electron. These alkoxy group shows electron withdrawal by induction plus electron release by resonance. So ultimately we say this is electron releasing, because plus R effect always dominates over minus I effect. So this is electron releasing group. So these being electron releasing, we group say OR is activating group. Activating group means which increases the reactivity of ring towards substitution by increasing electron density. Whenever we have an activating group, electron density at ortho and para position is increased, so we say this is ortho para directing. That means electron density at ortho and para position is increased due to resonance. So when we say due to resonance, electron density is increased at ortho and para position, electrophilic substitution reaction will always take place at ortho and para position. So therefore we have this OR group. When this reaches with electrophile, this will give you substitution at para and substitution at ortho. But out of these ortho and para will be forming as a major compound, ortho will be forming as a minor compound. The reason is at this ortho, these two groups are close to each other, so this undergoes steric hindrance, means crowding effect. So because of this steric hindrance, ortho will be forming as a minor compound, but the major will be para compound. This is para compound. So para is major, ortho is minor compound. And we can have various electrophilic substitution reactions set. So we have looked at this OR. This reacts with chlorine in presence of FeCl3. We have chlorination at para position plus ortho. I am giving only the major compound. We have bromine in presence of iron, bromination reaction. Again bromination takes place at para position plus ortho will be forming as a minor compound. Then we have nitration by use of nitrating mixture. A nitro group is introduced at ortho and para position. Again ortho will be forming as a minor compound. Then we have sulfonation by use of sulfuric acid. We have sulfonation at para position plus we have ortho minor compound. Then we have reaction with alkyl halide in presence of AlCl3. This reaction is Friedel-Crafts alkylation, and again alkylation takes place at ortho and para position, so para will be forming as a major compound. Then we have R prime COX acylation in presence of AlCl3, when this gives you acylation at ortho and para position. These two reactions is known as Friedel-Crafts. This is alkylation, this is acylation reactions. All electrophilic substitution reactions will be shown by this, and the electrophile will always go to the ortho and para position. The reason being, due to this resonance, electron density at ortho and para position is increased without altering the electron density at meta position. So electrophile will easily approach ortho and meta position, para position, and due to steric hindrance, means due to closer distance between the two bulky group, this ortho compound will be forming in a lesser amount, whereas the major compound will be the para compound. This is electrophilic substitution reactions of ethers, aryl ethers. So this is all about the chemical aspects of the aryl ethers. Apart from breaking of this carbon oxygen bond, we can also have electrophilic substitution reaction of this benzene ring. So this is some chemical properties of ethers.